Hello everybody and welcome to chapter 3 of Advanced Functions, which is focusing primarily on rational functions now. You might remember a little bit about rational functions from last year. Chapter 3.1 focuses on the reciprocal of a linear function, so 1 over mx plus b, but we rewrote it a little bit, as you'll see in the next slide. In this presentation, I'll be going over how to analyze the function that we're given, how to find its intercepts, and as well as describe the graph of the function. So let's get started. First of all, we'll be analyzing the function itself. The reciprocal of a linear function has the form f of x is equals to 1 over kx minus c. The kx minus c is nearly identical to mx plus b, but as you could see we have a negative, but that doesn't matter, it's still the equation for a line. This form of function allows us to find a variety of information such as the domain, range, and its asymptotes. As you learned from last year and the previous chapters, finding the domain and range is rather easy, but here we have been introduced to the concept of asymptotes. If you don't remember what an asymptote is, essentially an asymptote is part of the graph where there's a break and then the graph either starts to follow the line but it never fully touches it, or like it nears closer and closer to it but never actually crosses it. So for the rational functions we get asymptotes. For this particular one, we have an asymptote at the point x is equals to ck. This will always be the case, as what we're actually doing is finding the value of x that would make the denominator equal to 0. As we know, we can't be dividing by 0, as that would provide an exception to all the math rules we've learned so far. Henceforth, we must find the x value that would make this whole thing not make any sense. When it doesn't make any sense, that's where we get our vertical asymptote. So when we find our vertical asymptote, which is, as I said, the value of x is equals to c over k, we could finally find its domain. For these types of questions, or these types of functions, I should say, the only place where our domain is restricted is at its vertical asymptote. Hence, we would say that x has to be an element of all real numbers, such that x doesn't equal to the value of c over k. Lastly, we get the range of the function by analyzing its behavior. You could first of all start thinking about how the function would behave if we choose like a really, really small number, like negative 1 million, or like a really large number, like an actual million, like a positive million. But then we also have to look at its behavior at the vertical asymptote from the left and the right. When you do that, you'll find that for no matter the case of x and c, you'll always have the same range, and that is y is an element of all real numbers such that y doesn't equal to 0. It is rather easy to find this exception or this restriction, because when you're looking for, when we're going to discuss the intercepts, you'll see why that doesn't work. Talking about the intercepts, just like for any function, you can always find the x and y intercepts by plugging in the y and x values, respectively. However, as I discussed literally 3 seconds ago, we have a horizontal asymptote of y equals 0, because as we look here, that's what it states, right? So the asymptote has to be at y equals 0. The reason for that is to find the horizontal asymptote, what we're actually doing is trying to find the value for y where this thing or this function is equal to 0, or a value that we cannot achieve. Since we have 1 as our numerator, we could have 1 divided by 1, 1 divided by 0.5, or 1 divided by 1.5. So we'll be going in a range of numbers that is going to be either growing bigger, bigger, and bigger, or growing smaller, smaller, and smaller. However, we will never reach the point where this function equals to 0, because we can't divide 1 by something to get 0. That is why we can't. That is the horizontal asymptote, and that is why the range is y cannot equal to 0. With that in mind, we could always find the actual y-intercept by simply plugging in x equals 0 into the equation and solving for y. As we know, we write the function as f of x, but we could say let y equal to, for example, 1 over 3x plus 2. From here, we would substitute 0 into the equation, so we get 3 times 0 plus 2, 1 divided by that, which is 1/2. Therefore, our y-intercept is 1/2. Again, you learned this back in like grade 9, so this shouldn't be a very difficult concept for you to handle. Lastly, we have our mission of describing the graph. So when you're working with rational functions, it's important to learn how to describe key features of the graph, as well as use those features to write the corresponding equation. That might sound a little bit complicated, but I will let you know it's not that difficult. So first of all, when looking at the function itself, you can easily find the behavior of each branch of the function by analyzing the k-value. If you're not sure what I mean by the branch, I mean these segments as part of the function. They are independent from each other, like they don't intersect, that's why we just call them branches. So if we look at the k-value and it is greater than 0, the left branch of a reciprocal linear function has a negative decreasing slope, and the right branch has a negative increasing slope. And when we look at a function where k is smaller than 0, the left branch of a reciprocal function has positive increasing slope, and the right branch has a positive decreasing slope. Again, it might be a little bit difficult for you to understand how this happened. You could again start choosing your x values and analyzing whether or not the x or the y values are increasing or decreasing. But I personally find this little diagram a whole lot more useful, which is why I put it here. So let's look at example 1, where we had k is greater than 0. So this is just a generic form where we set k is some value above 0 and c is any value we want it to be. So what we have actually is we have these two branches. I put these two lines to help us visualize what's happening. We're going from negative infinity to our vertical asymptote, which creates the following downward line. As we know, a downward line like this would mean it has negative slope, right? So that's where we're getting the negative part over here. Then we have the actual function itself. We were strong close to 0, and then we started going to negative infinity. So we started decreasing in our y values as we came closer to the vertical asymptote. That is where we get the decreasing slope. Now let's look at the other branch. We're still going downward, which means it is a negative slope. However, this time we're coming from positive infinity to the vertical asymptote, and as you can see, the value started to increase. Therefore, we get the increasing slope part. Looking at the other function, where k is smaller than 0, and c still any other value, our first branch, our left branch, is now positive. And the y values are now going from small values to very large values, which means it is increasing. Now, we look at the second branch, we still have a positive slope. And now, if we look at the values as we're going from the positive infinity to the vertical asymptote, the values are now decreasing. Therefore, we get a positive and decreasing slope. With all of that in mind, these are the homework questions I've assigned for today. I have decided that I will simply be going over how to do them once more, and then that's about it. This whole chapter again is just testing your understanding of the pure concepts that are given to you. There's not much for actual application questions, or I shouldn't say application questions, but questions that require you to fully analyze a word problem like we had in chapter 1, or like with graphing. That is why I'm choosing not to go over each and every question. However, if I see a question that is a little bit more detailed, I will try to explain it as proficiently as I can. So let's get started on the homework. Okay, so let's look at question 1. Copy and complete each table to describe the behavior of the function as x approaches each key value. So the reason why we have 2 plus and 2 minus, it means we're approaching 2 from the left side and the right side, as well as when x is approaching positive and negative infinity. So when we're looking as x approaches 2 from the positive side, which would be from a value that is greater than 2, so for example 2.1, we would get a positive value, 1 divided by a positive value, and as this value gets smaller and smaller and smaller, so with the value at the denominator, which would mean we're dividing 1 by a very small number, but a very small positive number, which would mean this is positive infinity. Now if we look at a value that's a little bit smaller than x, this would be a really small negative value. So 1 divided by a really small negative value would give us negative infinity. Now as x approaches infinity, what we actually get is 1 divided by a very big number in general, and when we're dividing 1 by a very big number, we would get 0. Again, we have negative infinity here, so we have 1 divided by a very big negative value, which would mean a very small negative value, which would approach to 0. So our answer would be positive infinity, negative infinity, 0, and 0. You could apply the same strategy for B and C, that's why I didn't include them for the solutions. Now I've assigned 3, A and D. So for each reciprocal function, write an equation to represent the vertical asymptote, write an equation to represent the horizontal asymptote, and determine the y-intercept. So for question A, the vertical asymptote can be found by making the denominator equal to 0. So x minus 5 is equals to 0, so x is equals to 5 is the vertical asymptote. The horizontal asymptote, as we discussed before, will always be equal to y is equals to 0. With determining the y-intercept, all we're doing is substituting x equals 0 into the equation, so we say let x equals to 0, so then we have f of 0 is equals to 1 over 0 minus 5, which is negative 1 over 5. And that's our solution for A. For D, you're doing the exact same steps. So again, we're looking at a value at which x plus 7 is equals to 0, which would be x is equals to negative 7. With these types of equations, y equals 0 is always the horizontal asymptote, and to find the y-intercept, we'll let x equals to 0, so our y-intercept is y is equals to negative 1 over 7. Now let's look at question 5. Determine a possible equation to represent each function shown. I've assigned 5c. So first of all, we immediately know what our asymptote is, and that is x is equals to 1 over 2. With that, we need to find the denominator. So we rearrange this, so we get a 0 on one side. To do that, we first of all multiply both sides of the equation by 2 to eliminate the denominator, so we get 2x is equals to 1. Then we move the 1 to the other side, so we get 2x minus 1 is equals to 0 as our denominator. Since we know our denominator, all we need to know now is our top value, which we could find by substituting in our y-intercept. So our y-intercept is -1. So -1 is equals to a, that's what I'm calling the numerator, a divided by 2x minus 1. However, we know that x here has to be 0. So we get -1 is equals to a divided by 2 times 0 minus 1. So -a is equals to -1. So a is equals to 1. Therefore, a full equation would have to be y is equals to 1 over 2x minus 1. Now, with that out the way, let's go look at question 7. All of these ones are very similar, just sketching each function, describing the intervals. It's the same thing. So question 7 actually does the exact same thing with more complicated questions. So we have to sketch the graph of each function, label the y-intercept, state the domain and range, and the equations of the asymptotes. I assigned A, C, and E. I will do question E for you, and the other two you could do by yourself. Okay, so I wrote the question down for our example here. We have f of x is equals to -3 2x minus 5, and we have to sketch it and find all of its values, so like the x and like the y-intercepts, and also the equation for its asymptotes. So first of all, let's get a nice graph going. This is our y values, this is our x. First of all, we could immediately find our VA, where we found that 2x minus 5 has to equal 0. So 2x is equals to 5, x is equals to 5 over 2. This is our vertical asymptote. So let's say this is 1, this is 2, this is 3. So our vertical asymptote is over here, and we say this is x is equals to 5 over 2. Next, what we have is we have -3 2x minus 5. So we could find our y-intercept by saying that let x equal to 0. So m of 0 is equals to -3, 2 of 0 minus 5, which is equals to -3 over -5, which is equals to 3/5. So our intercept is at 3 over 5, which I'd say is around over here. Come on. Sorry. Let's do a line. There you go. That's our y-intercept, and we need to label it. So y is equals to 3 over 5. Now, we need to think about what that negative does and what we could possibly be doing here. Can this equation equal to 0? So let's see. 0 is equals to -3 over 2x minus 5. That can't happen, therefore our horizontal asymptote is at y equals 0, like it always has been. What we have now is the following. We have our y-intercept, and we know it can't go below or can't intersect the y-axis. Also, there's a plane flying by, so it's probably again really loud. So the only solution, or the only way to graph this branch, would be by the following. This is branch 1, right? Now we have our second branch, which would have to be like this. So we're going from -infinity to 0. That is the equation, or the graph of this function. The domain I think it was asking for is rather simple. X is an element of all real numbers. Sorry, that's a really bad element. Element of all real numbers such that x cannot equal to our vertical asymptote, which was 5 over 2. Our range is, as it always has been, y is an element of all real numbers such that y cannot equal to 0. Lastly, it was asking about the asymptotes. As we stated here, we have our vertical asymptote at x is equals to 5 over 2, and then our horizontal asymptote is that y is equals to 0. If you follow this procedure, you should easily be able to solve question A and C of number 7, as well as any other question in this chapter. Now let's look at question 10. Question 10 is a word problem, which might be intimidating at first, but I promise you we will get through this hurdle together. So the question asks us, the time required to fly from one location to another is inversely proportionate to the average speed. When the average speed to fly from Quebec City to Vancouver is 350 kilometers per hour, the flying time is 11 hours. A. Write a function to represent this time as a function of the speed. B is sketch a graph of this function. And then C is how long would the trip from Quebec to Vancouver take as an average speed of 500 kilometers. And lastly, we have describe the rate of change at the time the average speed increases. Okay, so let's do it here. This seems good, except I'm just gonna zoom that in once I remove all of these. This is honestly my favorite part. Also, put point 1 back. Give me a second. Okay. Write the function. Sounds good. Okay. So what we know is we're dealing with distance, the speed, and time. So what we know is distance is equal to speed times time, right? So d is equals st. So our distance is actually equal to the 350 times 11, I'm pretty sure, if I'm not wrong. Just give me a second. Yeah, 11 hours. So d is equal to 380 that. Since we have the following, we have to write the function to represent the time as a function of the speed. Also understand I should be using v, but sorry, speed was just easier to write than s. So what we will have to do is we would say time is equal to our distance over time, right? Because to isolate for time, we do distance divided by c. So it's 380 that over the speed. That is our solution for A. For B, it is asking to sketch a graph of this function. So what I would do personally is, since we're dealing with a real life problem, I would not include the negative y and the negative x, as they don't make any sense within a real life problem. Now, what we know is that it is a reciprocal function or rational function. We know that it would be going from the following, where we start up high. When time equals to 0, we would be at nowhere, but it'd be really close to infinity. And then we'll be going down like that, where we try and reach 0. We know that if x is equals to 2, we would get the value of 1925 when x is equals to 2. So I'll just graph that to show this is the exact function we're dealing with. Next, it's asking us to figure out how long would the trip from Quebec to Vancouver would take at an average speed of 500 kilometers. So we're substituting the value of s equals to 500. So t is equals to 3,850 divided by 500, which is approximately 7.7. Is it approximately? I think it's just 7.7. 7.7 hours. So you could either write that or you convert that to minutes, but unless the question is specifically asking for minutes, I don't think it's necessary, so we're gonna let it be like that. Lastly, we need to describe the rate of change as the average speed increases. So let's just think about this logically. If you're going faster and you're covering the same exact distance as you were before, your time should be decreasing, right? That is all this question is asking. Therefore, we would just say, as the speed increases, the rate of change of the time would decrease. And that is it for question 10. Now let's look at question 13. The force required to lift an object is inversely proportionate to the distance of the force from the I can't read that word, of a lever, so I'm not even gonna try. A force of 200 newtons is required at a point 3 meters away from the bird to lift a certain object. See, this is why math is so beautiful. You don't actually have to be good at English to understand what's happening. So for question 8, we have to determine an equation to represent the force as a function of the distance. Then we have to sketch a function of this function. And lastly, then we have to figure out how much force is required to lift this object for 2 meters away from the point, and what effect the force needed as a distance of the function. What effect on the force needed as the distance from the fulcrum is doubled. Okay, so this question seems to be really close to question 10. So what we have at first is we're learning that a force is inversely proportional to the distance of the force from a fulcrum over of a lever. So what we'd have to do is say that the force is equal to 200 times 3, since that's our the function is equals to 200 times 3, which would be our fulcrum force. Sorry, I just need to read this to find the actual third variable. The force required to lift. Okay, so for question A, we're determining a function to represent a force as a function of the distance. Okay, so what we know at first is that a force of 200 newtons is required at a point of 3m. So we could say that F is equal to force times the distance, which would equal to 600. And since we know this is an inversely proportionate relationship, what we could actually say is that the force, so like, I don't know, capital F, is equals to F, so the actual force times distance at the fulcrum is equal, divided by d would equal to the function. So our answer would be force is equals to 200 times 3 divided by the distance, which is the same as saying F is equals to 600 over d. Now we're sketching a graph of this function. We already know how to do that, so you could go ahead. Now our question is asking us how much force is required to lift this object at a point of 2 meters. If we have the distance equals to 2, we just simply plug it into the equation. So we get F is equals to 600 divided by 2, which is equal to 300 newtons. Therefore, our force is equals to 300. Lastly, we have the question asking us what is the effect on the force needed as the distance from the fulcrum is doubled. So now, what we're saying, instead of d, we have 2d, right? So now we have our equation equaling to F is equals to 600 divided by 2d, which is the same as F is equals to 300 divided by d, which actually halved our force in half, or like it just halved our force, and that would be the answer. With that last question out the way, this concludes our lesson for chapter 3.1, the inverse of a linear function. As you can see, this chapter was rather simple, next class we'll be discussing a topic that's a little bit more detailed. However, it's nothing difficult either, so I can't wait to help you out. I hope you had a lot of fun listening to this lesson, and I can't wait to see you next time. Thank you.